So we started by writing down all of our knowns and all of our known equations, and we created a free body diagram as well as a kinetic diagram. And our free body diagram, there's only one because we assumed that the objects were already in motion, so that none of them are touching, so they're all the same.
So from our previously known equations, we know the sum about the moment g, and we also know I is equal to mk squared. So using our free body diagram that was previously drawn, we can substitute these values in here and get that alpha is equal to gr sine beta over r squared plus k squared.
So now that we have our angular acceleration, we're going to convert it into linear acceleration. So we get the equation r squared g sine beta over r squared plus k squared.
So from our previously known equations, we know that kp is equal to r, so substituting into our previously solved equation, we'll have this one here. Further factoring, we'll be left with 1/2 g sine beta, and then our final a of pipe is going to be equal to 0.8517. Alright, so once again, we have the same process but a different k value. So substituting that in once again, we'll be left with 2/3 g sine beta, and our final acceleration of the cylinder will be equal to 1.1357. So once again, we'll be working with the same equation. Instead, we're subbing in the k value for the sphere, which will give us 7/5 g sine beta, and therefore the acceleration of the sphere will be equal to 1.2168.
So now that we have the acceleration for all three objects, we're going to find the acceleration between the cylinder and the pipe by subtracting the pipe's acceleration from the cylinders. That will give us a final result of 0.284. Okay, so we're going to run through the same process but with the accelerations between the sphere and the cylinder this time. So we will get a final acceleration of 0.0811.
From our previously known position equation, we'll be left with the position being 1/2 at squared. And since we have time and we have a previously solved acceleration, we'll be left with a clear distance after 4 seconds of 2.272 meters. So once again, we have the same equation but different variables to plug in. So we'll be left with a clear distance between the sphere and the cylinder to be equal to 0.6488 meters after 4 seconds.
So finally, we're going to be solving for the coefficients of frictions. And first we'll need the linear velocities of each object, which we found using v equals at. Then we need to use, from the free body diagram, the sum of the forces in y to get that the normal force is equal to mg cosine beta, which can be plugged into the force of friction equation here, which will finally give us a sum of forces in x of mg sine beta minus mu mg cosine beta. Plugging that into the impulse momentum equation, which does not have the initial velocity because it started from rest, we get this final equation where when we rearrange the variables, we get mu is equal to g sine beta over cosine beta minus vx2 over t2. So now that we found the general equation for the coefficient of friction, we plugged in the numbers for each of the objects so that we get a coefficient for the pipe of 0.8781, the coefficient for the cylinder of 0.5941, and the coefficient for the sphere of 0.5130. And that can be seen in our solution down here, along with the solution to part A, distance between the cylinder and the pipe, 2.272 meters, and the distance between the sphere and the cylinder, 0.6488 meters. And that's how you solve the problem.